Hello friends, welcome to follow up. In this video, let's have a look at problem 2685. Count the number of complete components. This problem actually is a graph problem. The main point is to get the connected components and then check completeness. So due to the problem nature, actually there are two typical methods to address this problem. So one is based on traversal. So we can use breadth first based solution, or we can use depth first based solution. So this is the one route. Another method is union find. So basically, traversal and union find are the two typical methods for finding connected components. So in this video, we are going to explain a solution based on traversal. First, let's briefly look at the problem statement. We are given an integer n, and there is an undirected graph with n vertices numbered from 0 to n-1. So in other words, here we are using zero indexing. We are also given a 2D integer array called edges, where edges I equals ai bi, indicating that there exists an undirected edge connecting the two vertices ai and bi. So our task is to find the number of complete connected components of the graph. So next paragraph basically explains what's complete. So a connected component is basically this is the explanation of connected component. So the last paragraph explains what's completeness. So a component is said to be complete if there exists an edge between every pair of its vertices. So basically, the big structure for a solution to this problem is that we first find the number of connected components, then we check if they are complete, then we return the corresponding complete connected components. So here we are required to return the number of such connected components. So if we look at the examples here, in example 1, so we see there are 3 connected components. So actually, the first one with a single node is very special because they have 0 edge due to the number of nodes, right? And in example 2, we return 1. The first one, 0, 1. So this is the nodes in the connected component. It's complete because there is an edge between any 2 vertices. But for the second one, consisting of nodes 3, 4, 5. So for example, there's no edge between node 5 and node 4. Here, by no edge, we mean direct edge. So the constraints for this problem are the following. First, n is bounded above by 50, and the number of edges is bounded by this combinational number, that is, choose 2 from n, right? So the edges I length is 2, and ai and bi are in between 0 and n-1, and no self-edge, and no repeated edges. So with that said, basically we are ready to do the coding part. So in between, we are going to explain the logic and the implementation detail. So here, let me first write something. So here, the method is based on traversal. So as for traversal, you can use breadth first search or depth first search based method. So for locating connected component, for finding connected component or components, so typically two lines of method. So one is traversal, and the other is union find. So these are the 2 typical methods or common methods. So here we are going to use depth first search based traversal algorithms. Here the overall outline is like this. First, we're going to build a graph, and then we're going to write utility functions to do DFS. In other words, locating connected components. Third one is a utility function to check completeness. And finally, we are going to do the return, right? So this is the outline. So now let's move to the implementation. So let's look at the first step and build the graph. So when we build the graph, we need to pay attention to some isolated nodes, like the 5 in example 1. So we're going to use this. So the graph equals I, and we use an empty set. So for I in range M, right? So then we're going to traverse the edges. So basically for UV in edges. So we're going to do this. Graph U at V and graph V at U. The reason we do these 2 lines of codes is due to the fact that the graphs are undirected or bidirectional. So this is the first step, building the graph. And then the second second part will be a utility function to do connected component location. So we want to find all the connected components. So we're going to use a DFS function. So here we are writing this in terms of utility function. The thought or motivation behind is to make the logic clear, right? So we split the code into different ingredients. So now let's implement this function DFS. So we're going to have a source, right? And then we're going to define a set called visited, initially empty. So we're going to return the final state of this set. Basically, we want to use the nodes to represent the corresponding connected component. Sorry, let's see. Visited is a set, and then we're going to use depth first search. So we're going to use a stack, and let's use it, name it as S. And then basically we do the while loop. In other words, I'm writing this code in an iterative format. So let's first get the current node, that's S pop. So then if node not in visited, so we're going to add this node to visited, and then we're going to check its neighbors. So for neighbor in graph node, so if neighbor not in visited, so we're going to put it in the top of the stack, that is S append node neighbor. So after this while loop, we're going to have a final state of the visited set. So this is a representation of the corresponding connected components. So here, before we write the utility function to check completeness, let's use C2 prime to start. That is call DFS to get the connected components. So this is actually very simple. Let's first use a big set to avoid repetition. Then I will call this clusters. And then we're going to do the iteration. So for I in range M. So we want to check if I not in visited. And then we're going to get the cluster with the I as the source, that is DFS I, right? So we're going to clusters append. So add this cluster to the list clusters, and then we're going to update the visited by union it with the current set C. So the nodes in the visited are actually visited ones. In other words, in the connect components, we don't need to do the repetition, right? So this is the second auxiliary step, right? So we wrote the utility function, and then we called the DFS function to get the connect components. So the third step as we mentioned above, so we're going to write a function to check completeness. So this actually can be very routine. So just let's see, define complete. So here we are going to accept a cluster or connect component. So notice that C is a set, right? And then basically we want to see for I in C, right? And for J in C. Let's write without any delicate thought. So then we want to check if J equals I. This same node, just continue, right? Otherwise, so if J not in graph I, yeah, you can also check I not in graph J, right? So we just return 0, right? So if after this traversal or for loops, so nothing has returned, so we're going to return 1. So in other words, 0 means not complete. 1 means a complete connected component. So with that said, basically we can do the return for this problem. So let's see, for its return, we can use list comprehension, or we can use comprehension because we want to return the counts, not the specific components. So here we're going to do sum, and then we check complete of the cluster or component for cluster in clusters. So this actually forms a solution format to this problem. So this way of writing actually is very verbose. So we break the solution into several ingredients by building graph, utility function to get connected components, then we call the utility function, and then write utility function to check completeness, and then we call this complete function to get the final counting. So before we make any comments, let's first do a check. Yeah, it passes the first example. Now let's directly check the generic case. Yeah, it passes all the generic cases. So when we do the check, actually it's important to notice this case. So if J equals I, so this is actually corresponding to such cases like note 5 in example 1. Such cases are sort of edge cases. It's regarded as complete. So with that said, basically that's about it for the traversal based solution to this problem. Actually, this problem can also be solved elegantly using disjoint set data structure or the unified method. So you can have a try. So with that said, basically that's about it for this video. Thank you.